about how we designed our bridge and why, then how we built it, the challenges we had building it, and how we changed it, and then what we learned throughout the course of this project.
The first thing we decided when building our bridge was that we wanted to use as much balsa wood as possible and very little popsicle sticks, because popsicle sticks are a lot heavier. The first thing we designed was the span of our bridge. We experimented with various truss types in the Model Smart program, and we eventually ended up with a simple Xed truss. There are internal supports on our bridge to help strengthen the cross beams. It's 2 inches wide on the top and 1 inch wide on the bottom. The angling in helps cut down on weight, as well as helping with force diversion. The next thing we designed were the bases. They're almost triangular pyramids in structure. There are underlying supports that connect from the side, and they connect to both the towers and to the bridge span to help stabilize it. In order to strengthen our bridge span, we designed a series of underlying supports with lattice-like structures. The smaller ones are less detailed, but since the longer pieces are more vulnerable, we have them more complex in the internal structure. The ones to the very center of our bridge are the most important, as the center of our bridge has no cross beams or internal structure. The last thing we designed was the towers. We have them as 2 sections high, created to withstand as much horizontal and vertical force as possible. They are angled outwards slightly to help with the horizontal force. We wanted them both to be triangular in structure, however, this would not allow for the testing block to pass through. So we went with a box base and then moved it to be more triangular up top.
Now, this box base is one of the very few things on our bridge that is not triangular. As you can see, each of the X's creates triangles, and the internal supports are triangles. Everything on the underlying structure is triangles. Our bases are triangles. Triangles are very good with balsa wood because they withstand compressional and tensional forces very well. And when a load is placed on top of a triangle, it creates compressional forces in the legs and tensional forces in the bases. Now, we wanted our bridge to be an arch because when a load is placed on top of an arch, it diverts all forces into the bases. However, to have a very good arch, it would have to be too high for the height constrictions. So instead, we use the underlying supports more as tangent lines to the arches. So from the longest ones to the shortest ones, when we place them all together, it's like an arch, but it's all on one plane. And we also have made the top of the bed 2 inches wide exactly, because that's how wide the block is. And then the block would be touching as much of the balsa wood as possible and diverting as much of the force into the truss as possible. So we had to change the towers slightly to make up for that, and we'll talk about that later. And when we constructed the bridge, we did it in the same order as we designed it. First we did the span, constructing the X trusses, then the bottom and top and internal supports, adding on the bases, then taking all of the underlying supports, constructing them separately, then gluing them on, and constructing the towers last. Some of the problems we had with it were there are a lot of pieces on the inside that are really difficult to get to. So I had to do most of that because I have the littlest fingers. We also had a couple of pieces that were very, very small that were difficult to put in. And since so much of our bridge is at an angle, all the pieces had to be cut at an angle to attach them properly. So that was difficult.
Okay, when we built our bridge, we made 3 main changes from our original CAD drawings and program that we designed. The first one regards the towers, the second with the bases, and the third with how the strings are attached. The first one is the towers. On our original program, we had them built straight off of the top of the base. However, this created a slight problem. When they were built, it would be 2 inches from the outside of the tower to the outside of the other side of the tower. So we had to add second change of the tower was in our original designs, we had three segments of height to each tower. And the goal of this was to have the top of the tower as high as possible so the cables could pull up on the bridge as much as possible. However, when we converted it from the square base to the triangles in each tower, there were weak points where this changed, where it was converted, and also at the top. So to cut down on the weakness and increase the strength, we deleted the top segment of each tower and strengthened the back corner where all the weight was. The second change was in the bases. At the end of each span, our original plans had isosceles triangles that looked like this from here to there. That was originally going to be an isosceles triangle. However, we had all the underlying supports converge into a small area that we put on a popsicle stick. And had we had an isosceles triangle, all the underlying supports would converge on a point that would not be supported by the Pittsco tester. We decided that since the underlying supports took the majority of the bridge weight, we wanted them to be on the support directly on top of it, so their weight would be grounded. Also, we added the popsicle stick to secure all the points. The third change was the strings. On our program, there was no material that could account for the strings, and as it was a cable stay bridge, we had to put them on. So we used popsicle sticks underneath the top part of our span and connected them there. We used popsicle sticks there instead of balsa wood because popsicle sticks are a lot denser, and with balsa wood, the string on that can make it into a noose and choke it off and sometimes cut it. So when there's tension added, balsa wood does not support the bridge. Also, we attached them outside the span of our bridge so the block could pass through. Finally, we learned a lot of lessons in this. First off, we do not all think alike, so it was a challenge at times to come up with ideas and work them out. So we had to learn a lot of teamwork there. Another problem we had was scheduling. Since there were so many parts of the bridge, and each one had to take hours, I don't know how long exactly, but a long time to dry, we had to build each part in segments, and that took many days. So we had to schedule time in our study halls and after school, and sometimes before school to build it. While building this, we also learned a lot about the different bridge types, like the cable stay, and also the arch design that directs all the weight into the ground. Finally, we realized that sometimes we take a lot of bridges and other architecture for granted, because while building this, we did not have to worry about cost, construction people, weather, or anything else that real bridges have to do. On top of that, real bridges have to work. This test tells it breaks. Real bridges have to work, otherwise people can die. Finally, we had a rewarding feeling after finally finishing this bridge. At the testing, we already tested. It held 68 pounds.